Lesson 4.5: Evaluating and Testing Your Model. Overview: training is complete, but complete doesn't mean good. A model that trained without errors could still be producing garbage outputs, overfitting to your examples, or barely improving over the base model. This lesson is where you find out. You'll test your fine-tuned model with real prompts, compare it head-to-head against the base model. Read your training metrics like a diagnostic chart and build a clear picture of whether your training succeeded or whether you need to go back and adjust. Plan for about 30 to 45 minutes and come in at an intermediate level. By the end, you'll know exactly what a well-trained model looks like and what to do when it isn't. Learning objectives. Here's what you'll walk away with. You'll know how to test your fine-tuned model against new, unseen examples, not just the data it trained on. You'll be able to run a side-by-side comparison between the base model and your fine-tuned version so the improvement is concrete and measurable. You'll read your validation metrics with confidence, spot the difference between healthy training and overfitting, and know when a model is ready to ship versus when it needs another round. And you'll build a reusable set of evaluation test cases you can run against any future model you train. Loading your train model. If you're still in the same Python session where training happened, the model is already in memory. You just need to switch it from training mode to inference mode. That one call, fastLanguageModel.forInferenceModel, does more than it looks like. During training, the model runs with features like dropout active. Those are deliberate sources of randomness that help prevent overfitting. For inference, you want none of that. This call disables those features and optimizes the internal compute graph for generation. When you see model ready for inference printed, that's your confirmation the switch happened cleanly. Don't skip this step. Running inference on a model still in training mode gives you degraded, inconsistent output. If you're starting a fresh session or you want to load a saved model from disk, this is the pattern. Write single quote fastlanguagemodel.frm _ write single quote points at your saved model directory models/my _fine-tuned_. The max_seek_length of 2048 tells the model how much context it can work with at once. Keep this consistent with what you use during training or you'll get unexpected behavior. Load_in_4 bit $true keeps memory usage low, which matters on your P40S when you're loading two models simultaneously for comparison. After loading, the for_inference call switches the model into general. The confirmation print at the end is just a sanity check, but on a machine with multiple GPUs, it's worth having that explicit signal that the load completed without silent errors. Checkpoints are snapshots of your model's weights saved at specific training steps. Loading outpost/checkpoint 100 means you're evaluating the model exactly as it was after 100 gradient updates, not the final version. This is powerful for diagnosing training problems. If your final model is worse than checkpoint 100, that's a textbook overfitting signal. The model kept training past its optimal point. The rest of the loading pattern is identical. Same max_seek_length, same load_in_4 bit, same. The only thing that changes is the path string. When the confirmation prints, you're ready to run inference against that specific moment in training history. Creating test cases. Before you run a single inference call, you need to decide what good looks like. That's what test cases are for. Each test case here is a dictionary with 3 keys, a name so you can identify it in output, an input string that simulates the kind of text your model will see in production, and a list of expected fields, the specific pieces of information the model should extract. Notice the variety. One case is a clean, simple extraction. Another has multiple entities. another has incomplete information. One involves numerical data. This spread matters. A model that scores perfectly on clean inputs but fails on edge cases isn't production ready. Defining your expectations before running the model keeps you honest. You're not retrofitting the criteria to match whatever the model happened to produce. Testing function. The test underscore model function is the core of your evaluation loop. It starts by applying the tokens, measure units, llama, decimal, integer part 3, fractional part 1. Your model was trained with inputs formatted in a specific way, and if you feed it raw text at inference time, you're changing the distribution it was trained on. The chat template wraps your prompt in the exact structure the model expects, which is why responses come out clean and consistent. Inside the function, max underscore tokens caps response length so you don't get runaway generation, and temperature controls randomness. Lower values give you more deterministic output, which is what you want for structured extraction tasks. The use underscore cache equals sign true flag enables KV caching, which speeds up generation significantly. After generation, the output is decoded and stripped down to just the assistant's reply. No special tokens, no prompt echo. When you run this with the John Smith test prompt, a correctly fine-tuned model should return a tight JSON object with name and age. If you get a paragraph of prose instead, that's your first signal that something needs attention. Comparing base versus fine-tuned. Vasi choosati pas sen choose. To know how much your fine-tuning actually helped, you need a baseline. And that baseline is the original llama-3.2-3b- instruct model before any of your training. Loading it here with right single quote fast language model .fr om underscore preprened right single quote uses the same parameters as your fine-tuned model max underscore seek underscore length of 2048 and load underscore in underscore 4-bit equal sign true. On your dual P, after loading, 4 underscore inference puts the base model in generation mode. The confirmation message tells you the load succeeded. Now you have two models ready. Same architecture, same quantization, same inference settings, and the only difference between them is your training data. That isolation is what makes the comparison meaningful. The compare underscore models function runs the same prompt through both models and prints the results side by side. For the base model, it manually tokenizes and generates, applying the chat template and the same max underscore new underscore tokens and temperature settings you'll use for the fine-tuned model. For the fine-tuned model, it calls your test underscore model function directly. The reason you want both outputs on screen at the same time is that the difference is usually striking. Base models tend to be verbose and inconsistent. They might answer correctly one run and completely differently the next, or they might explain their reasoning in paragraphs when you wanted a JSON object. Your fine-tuned model, if training went well, should be concise, structured, and consistent. That contrast is your proof of work. Here's what that contrast looks like in practice. The base model, given a prompt about Sarah Jones, tends to respond verbosely and inconsistently. It might write a sentence, list bullet points, or format things differently on every run. Notice what the base model is doing here. It's extracting the right information, name, age, profession, workplace, but it's doing it in prose, not structured JSON. The format is unpredictable. If you ran this 10 times, you'd likely get 10 different formats. That inconsistency is the problem fine-tuning solves. The model understands the task, but it hasn't learned the output contract your application depends on. Now here's what the fine-tuned model returns for the same prompt. This is exactly what you trained for. A clean JSON object, name, age, occupation, company, no preamble, no explanation, no variation. Every field is present, every key is correctly quoted, the structure is machine passable. This is the output contract your downstream application can rely on. When you see this from your fine-tuned model and compare it to the base model's prose response, that gap is the measurable value of your training. If your fine-tuned model is producing output that looks like this, you're in great shape. Analyzing training metrics. Acetate Pew. Your training run saved a file called write single quote trainer underscore state.json write single quote inside your output directory. This file is a complete log of everything that happened during training, every loss value, every evaluation step, every metric the trainer recorded. This code opens that file, passes it as JSON, and walks through the log history to pull out two things: the training loss at each step and the validation loss at each evaluation checkpoint. These get stored in separate lists so you can plot them. When the code prints how many training steps and evaluation points it found, check that those numbers match your training configuration. If you ran 200 steps with evaluation every 50, you should see roughly 200 training entries and 4 evaluation points. A mismatch here might mean training was interrupted or checkpointing wasn't configured correctly. Plotting these loss curves gives you the clearest possible picture of what happened during training. The first subplot shows training loss over steps. You want to see a curve that descends steadily and then flattens as the model converges. The second subplot shows validation loss at each evaluation checkpoint, with markers so you can pinpoint exactly which step each measurement came from. The validation curve is the one that tells you whether your model is actually learning generalizable patterns or just memorizing your training examples. The plot gets saved as a PNG in your outputs directory, which means you have a persistent record you can reference later or include in documentation. After the save, the confirmation message tells you the file was written successfully. This is the pattern you want to see. Training loss starts around 3.0 and drops steadily to 0.6. Validation loss tracks it closely, starting at 3.1 and landing at 0.7. The two curves move together, and the gap between them stays narrow throughout. That parallel descent is the signature of a model that's learning real patterns, not just memorizing your training examples. When validation loss stays close to training loss all the way down, it means the model's improvements on training data are transferring to data it's never seen. This is healthy training. If your curves look like this, you're ready to move forward. This pattern is a warning sign. Training loss drops all the way to 0.1, extremely low, but validation loss tells a completely different story. It starts at 3.1, dips slightly, then climbs back up to 2.5. That divergence is the textbook signature of overfitting. The model has essentially memorized your training examples. It can reproduce them almost perfectly, but when it sees new text, performance degrades. The fix is not to train longer, that will make it worse. Your best model is sitting in whichever checkpoint had the lowest validation loss before it started climbing back up. Load that checkpoint, not the final one. When you see overfitting, you have 3 levers. First, use the checkpoint where validation loss was lowest. That's your actual best model, not the final weights. Second, add more training data. More diverse examples make it harder for the model to memorize rather than generalize. Third, increase regularization. Raising weight underscore decay or adding dropout makes the model work harder to find general patterns instead of shortcuts. Usually, more data is the most effective fix. This third pattern is the opposite problem. Training loss drops from 3.0 to only 2.6, a modest improvement that's flattening out. Validation loss drops from 3.1 to 2.7, also still. Both curves are moving in the right direction, but neither has converged to a useful level. The model is learning, but not enough. This typically means the training run was too short, the learning rate was too low to make meaningful progress, or the LoRa rank was too small to give the model enough capacity to learn your task. The loss curves aren't diverging, there's no overfitting, so you have room to push harder. When the model isn't learning enough, you have 4 options, roughly in order of impact. Train longer with more epochs. The model may just need more passes over the data. Raise the learning rate so each gradient step makes a bigger update. Increase the LoRa rank, which gives the model more parameters to work with and more capacity to capture complex patterns. And always check your data quality. If your training examples have inconsistent formatting or incorrect labels, no amount of training time will fix that. Quantitative evaluation. The batch_test function automates what would otherwise be tedious manual testing. It takes your list of test cases and a model function, runs every test case through the model, and collects the results in a structured list. For each test case, it extracts the input text, calls the model, and records the name, input, raw output, and expected fields together. After defining the function, you invoke it with your test cases and the test_model function you built earlier. The printed output gives you a readable summary of each test, what went in, what came out. At this stage, you're reading the outputs qualitatively. The scoring comes next. The score_output function turns qualitative inspection into a number. For each expected field, it checks whether that field name appears anywhere in the model's output string and increments the score for each hit. The final score is expressed as a percentage of expected fields that were present. This is a simple but effective first-pass metric for structured extraction tasks. If the model was supposed to return name, age, and occupation, and all 3 appear in the output, that's 100%. If only 2 appear, that's 67%. The loop that follows runs this scoring function against every result from batch_test and prints each test case's name alongside its match percentage. Watch for patterns in the failures. If the model consistently misses one particular field type, that's a signal about what your training data needs more of. A result like this, most test cases at 100%, an average around 91%, is a strong signal that training worked. But don't let the average lull you into skipping the individual scores. The cases that scored below 100% are your most valuable data points. They tell you exactly which input patterns or field types your model struggles with. An edge case scoring 67% might reveal that your model handles simple extractions perfectly but drops fields when the input text is ambiguous or structured unusually. That's actionable. You know precisely what to add to your training data if you decide to retrain. Qualitative evaluation. Qualitative evaluation starts with a set of simple, known inputs where you already know what the correct output should look like. This JSON dataset, 3 people with names and ages, is deliberately minimal. You're not testing the model's knowledge here, you're testing its output format and consistency. When you feed each of these entries through your model, you should get back a clean JSON object every time. The value of starting simple is that any formatting error is immediately obvious. If the model can't handle 3 clean, unambiguous inputs correctly, you don't need to run the complex edge cases yet. 3 inputs, 3 outputs, and they're not all equal. The first output is correctly formatted JSON with properly quoted keys and valid structure. That's what you want. The second has a missing quote around the key age. That's invalid JSON. A downstream parser will throw an exception on that. The third isn't JSON at all. It's a plain English sentence. That's a complete format failure. 2 out of 3 outputs are broken, and they're broken in different ways, which tells you the model hasn't fully internalized the output contract. This is exactly why qualitative evaluation matters. Your quantitative score might look acceptable because the right words appear in the output, but the format is unusable. Both dimensions matter. There's a subtler failure mode worth watching for beyond outright format errors. A well-trained model returns exactly what you asked for, nothing more. A partially trained model sometimes adds commentary around the JSON. Phrases like "here is the extracted information" before the object, or "let me know if you need anything else" after it. That extra text breaks automated parsing just as surely as a missing quote. This is the clean output you're looking for. Just the JSON object, nothing else. No preamble, no explanation, no trailing commentary. The model understood the task and returned only the structured data. When you see this consistently across your test cases, it confirms that fine-tuning taught the model not just what to extract, but how to format and bound its response. Consistency across multiple runs matters too. Run the same prompt 3 or 4 times and check that the output format doesn't drift. Once your model handles the clean cases correctly, push it harder. Test with inputs where a field is genuinely missing. Does it return null, omit the key, or hallucinate a value? Test with ambiguous text where a reasonable person might disagree about the answer. Test with inputs that contain multiple entities to see if the model handles one, all, or none. Test with special characters and Unicode. Test with a single word input and a 1,000-word paragraph. The edge cases are where models fail in production, and finding those failures now, before deployment, is exactly the point of this evaluation phase. When training was successful, here's a concrete checklist for what a successful training run looks like across 3 dimensions. On loss metrics, your final training loss should be under 1.0, training, and validation loss should be close together, not diverging, and the loss curve should show a steady downward trend with no NaN values anywhere. On output quality, the model should produce consistent, correctly formatted responses, handle edge cases without falling back to prose, avoid hallucinating fields that weren't in the input, and show clear improvement over what the base model produced. On process health, training completed without out-of-memory errors, checkpoints saved successfully at the intervals you configured, and GPU utilization stayed in a reasonable range throughout the run. If all 3 dimensions check out, you're done here. The next lesson covers saving and sharing your model. When to retrain. Aventiyadi. If your model gets the right answer sometimes but uses the wrong format other times, JSON one run, prose the next, that's inconsistency, not ignorance. The model has learned the task but hasn't fully committed to the output format. The fix is usually more training, either more epochs over your existing data or more training examples that consistently demonstrate the correct format. Inconsistency is a signal that the model is still on the learning curve, not that it fundamentally can't do the task. When validation loss exceeds training loss by more than 0.5 and the gap is widening, you're looking at overfitting. The model has memorized your training set. Your immediate move is to load the checkpoint where validation loss was at its lowest. That's your actual best model. From there, you have 2 longer-term fixes. Add more diverse training data to make memorization harder, or lower the learning rate so the model updates more conservatively and is less likely to overfit on a small dataset. If your model's outputs consistently don't match the format you trained for, wrong JSON structure, wrong field names, wrong nesting, the problem is almost always in your training data, not your hyperparameters. Check that every example in your dataset uses exactly the format you expect the model to produce. Even 1 or 2 malformed examples can confuse the model about what the output contract is. Add more examples of the correct format and double check your prompt template to make sure it's consistent between training and inference. If your fine-tuned model's outputs are indistinguishable from the base model, same verbosity, same format inconsistency, no improvement, the training signal wasn't strong enough to move the weights meaningfully. The most effective fixes are raising the learning rate, training for more epochs, or replacing easy training examples with more challenging ones that force the model to actually learn the pattern rather than coasting on what it already knew. Complete Evaluation Notebook. This notebook brings everything together in one place. It loads your fine-tuned model with load underscore in underscore 4-bit for memory efficiency, applies the chat template to the token error, and defines the test underscore model function with max underscore new underscore tokens and temperature parameters controlling response length and determinism. A quick single prompt test runs first. That's your immediate sanity check that the model loaded correctly and is generating coherent output. Then the batch evaluation runs all your test cases and scores each one. Finally, the notebook loads write single quote trainer underscore state dot JSON, write single quote comma, plots the training and validation loss curves, and prints the final loss values as the visual output of those loss curves is what you'll reach for first when diagnosing any training issue. It tells the story of your entire training run at a glance. Evaluation checklist. Work through this checklist before you declare your model ready. On the setup side, the model loads without errors, inference mode is active, and the test function runs cleanly on at least one prompt. On the quantitative side, training loss is below 1.5, validation loss is below 2.0, and the gap between them is narrow. Validation loss significantly higher than training loss is overfitting. The loss curve should show a consistent downward trend, not oscillation or a rising validation line. On the qualitative side, outputs match the expected format. Test cases return the correct fields. The model clearly outperforms the base model on your specific task, and there are no hallucinated fields or malformed JSON. If everything checks out, you're ready to save and deploy. If something fails, the pattern of failures points you directly at what to fix before retraining. Key takeaways: 6 things to carry forward from this lesson. Always compare to the base model. Improvement needs to be concrete and measurable, not assumed. Watch your validation loss closely. It's the single most reliable indicator of whether your model will generalize. Test diverse cases, especially edge cases. Clean inputs will almost always work. Edge cases are where production failures hide. Visualize your loss curves. A 2-minute look at a plot reveals problems that would take hours to diagnose from raw numbers. Do manual review. Quantitative scores tell you how often the model is right, but only reading actual outputs tells you how it fails. And expect to iterate. A first training run that needs adjustment isn't a failure, it's the normal process. What's next? 2 paths from here. If your evaluation checks out, loss curves look healthy, outputs are clean and consistent, scores are strong, move forward to lesson 4.6, where you'll save your model in formats ready for deployment and sharing. If the model needs work, overfitting, format inconsistency, not enough improvement over baseline, head back to lesson 4.3 to adjust your training configuration with what you've learned here. Either way, you now have the diagnostic tools to know which path is the right one. Additional resources. Vares vant ve. Additional resources. Ve se do we tele se do we os. For deeper reading, look into model evaluation best practices for LLMs, techniques for comparing model outputs systematically, and the broader landscape of LLM evaluation frameworks. Your model is trained and evaluated. You're in the home stretch. Before you can evaluate your model rigorously, you need to know which metrics to reach for and when. Perplexity measures how confidently the model predicts the next token. Lower is better, and it's a useful signal for general language quality. RUSE measures the longest common subsequence between your model's output and a reference answer, making it the right tool for summarization tasks where you care about sequence overlap. BLU focuses on n-gram precision and is the standard metric for translation. Win rate is different in kind. Instead of comparing to a reference string, you pit your model against a baseline in head-to-head comparisons, often judged by a stronger model like GPT-4. Task accuracy is the most direct metric for structured tasks like information extraction. Does the output match the expected fields exactly or by F1 score? The key insight is that no single metric tells the whole story. For your information extraction task accuracy and qualitative format checking will be your primary signals. A radar chart like this one makes the comparison between base and fine-tuned models immediately intuitive. Each axis represents a different capability: domain knowledge, answer accuracy, tone consistency, task completion, and others. The fine-tuned model's polygon, shown in green, extends further out on most axes than the base model in orange. That visual gap is the concrete return on your training investment. Notice which axes show the largest gains. Domain knowledge and answer accuracy tend to improve most dramatically with fine-tuning on a specific task, because that's exactly what you're teaching the model. Axes like tone consistency and task completion improve because the model has learned your output contract. If you see an axis where the fine-tuned model regresses relative to the base, that's worth investigating. It might indicate that your training data was inadvertently teaching the model something you didn't intend. The evaluation pipeline has a clear sequence, and understanding the full flow helps you know where you are at each step. It starts with checkpoint selection. You pick the checkpoint with the lowest validation loss, not necessarily the final one. From there, you run your test set through the model to generate responses. Those responses feed into two parallel tracks. Automated metrics like RUDE scores and perplexity give you fast, objective numbers, and an LLM as judge approach, using a model like GPT-4 as an evaluator, gives you a win rate against your baseline. Both tracks feed into human evaluation, where a sample of outputs gets reviewed by a person. Typically 50 rows is enough to catch patterns that automated metrics miss. Everything converges into a final comparison against your baseline performance, and that comparison drives the deploy or retrain decision. This pipeline isn't just for your current model, it's a repeatable framework you can run every time you make a training change. Standard benchmarks give you a way to compare your fine-tuned model against the broader landscape, not just against its own base. MMLU tests general knowledge across dozens of domains. Human Eval measures code generation capability. HelloSwag tests common sense reasoning. Truthful QA measures how often the model produces factually accurate versus plausible sounding false statements. GSM 8K tests multi-step mathematical reasoning. The consistent pattern in these results is that fine-tuning on a specific task improves performance on that task, but it can also improve related capabilities because the training process reinforces general reasoning patterns. Watch for any benchmark where the fine-tuned model regresses significantly below the base. That's a signal that your training data may have inadvertently degraded a capability the base model had. For your information extraction use case, MMLU and truthful QA are the most relevant signals for whether the model is still grounded in accurate knowledge. RUDE scores give you a quantitative handle on how closely your model's text output matches a reference. Rouge 1 counts individual word overlap. A score above 0.40 is generally considered good. Rouge 2 counts two-word phrase overlap, which is more sensitive to phrasing. Above 0.18 is the target. Rouge L measures the longest common subsequence between output and reference, capturing sentence-level fluency. Rouge Alsum is the summary-level version, targeting above 0.33. Blue approaches the problem differently. It measures nagram precision, meaning how much of what the model said appears in the reference, and is the standard for translation tasks with a target above 0.20. For structured extraction tasks, these metrics are most useful as secondary signals. Your primary signal is whether the expected fields appear in the output and whether the JSON is valid. Rouge and blue become more central when your task involves generating free-form text that needs to match a reference closely. Perplexity is one of those metrics that's easy to misread. The graph here shows the relationship between perplexity values and human-rated quality. The green zone, perplexity between 1.5 and 5, is where well-trained models land, low enough to indicate confident, coherent generation. The yellow zone, 5 to 12, is acceptable but not optimal. The model is less certain about its predictions. Above 12 is concerning. At that level, the model is generating text that feels incoherent or unpredictable to human readers, but notice the warning at the low end. Perplexity below 1.5 is also a red flag. Extremely low perplexity means the model is almost perfectly certain about every token, which usually indicates memorization or overfitting rather than genuine language understanding. The healthy target is a perplexity that's low but not suspiciously low. Beyond numbers, you need a structured way to read your model's outputs qualitatively. This framework covers 7 dimensions. Correctness. Does the model answer the actual question, not a related but different one? Hallucination. Does it generate fields or facts that weren't in the input? Test this explicitly against inputs where you know a field is absent. The model should either omit the field or return null, not invent a value. Format. Is the output structure consistent across runs? Tone and style. Does the response personality match what you trained for? Edge cases. How does it handle ambiguous or tricky inputs? Refusals. Is the model refusing requests it should handle or handling requests it should refuse? And comparison. Put the fine-tuned model and base model side by side on the same prompt. The improvement should be immediately obvious. Running through all 7 dimensions takes about 20 minutes with a good test set, and it catches failure modes that no automated metric will surface. Your evaluation dataset is only useful if it's designed carefully. The most important principle is the holdout rule. None of your evaluation examples should appear in your training data. Even a single leaked example can inflate your scores and give you false confidence. The dataset should be representative of real-world queries. If your production inputs are messy, inconsistent, and varied, your evaluation set should be too. Include challenging examples, edge cases, ambiguous inputs, prompts that are slightly out of distribution. 50 to 200 examples is the right size range, enough for reliable metrics, small enough to review manually. Once you finalize your evaluation set, lock it and don't modify it. Changing the evaluation set between runs makes comparisons meaningless. Finally, spot check 10 to 20 outputs by hand on every evaluation run. Automated metrics have blind spots, and a human reading actual outputs will catch things no score captures. This radar chart adds 2 dimensions that the simpler comparison charts often leave out: speed and safety. The fine-tuned model in green outperforms the base model in orange on instruction following and accuracy. Those are the expected gains from task-specific training. But notice the speed and safety axis. Fine-tuning can sometimes affect generation speed if the model's internal attention patterns change significantly, and safety is worth monitoring because fine-tuning on a narrow dataset can occasionally cause the model to handle sensitive topics differently than the base model intended. The takeaway isn't that these regressions are inevitable, they usually aren't significant for task-specific fine-tuning, but they're worth measuring explicitly. If your application has latency requirements or operates in a domain with safety considerations, add those dimensions to your evaluation framework, not just task accuracy. When automated metrics aren't enough, and for high-stakes applications they rarely are, human evaluation gives you ground truth. The process starts with a rubric. 3 to 5 criteria like accuracy, helpfulness, and tone, each rated on a 1 to 5 scale. Prepare 20 to 50 diverse prompts that represent real usage. The critical step is blind comparison. Show raters the output from both the base model and your fine-tuned model without labeling which is which. This prevents bias toward whichever model the rater expects to be better. Use at least 2 or 3 raters and compute inter-rater agreement. If raters consistently disagree, your rubric needs to be more specific. Aggregate scores with 95% confidence intervals so you know whether observed differences are real or within the margin of noise. Review disagreements carefully. They often reveal ambiguities in your rubric or genuine edge cases where the model behavior is legitimately debatable. Document everything: model version, date, prompts used, and final scores. This record becomes your baseline for every future training run.